Alright, this is sample problem 13-47 from your book. It's going to give us some tabular data and ask us to write the rate law for the reaction. It's a nice problem because what it boils down to is analyzing experimental data that you're given through a graphical approach that we're going to talk about and figuring out what the order of the reaction is with respect to the reactant from the actual experimental data. Okay, so the problem reads like this. Consider the tabular data for the reaction. Substance AB, it's a gas phase, decomposes into A and B. It's these hypothetical elements. We could say, obviously, this is not a real material, but it's some reaction in which we have a decomposition, okay, unimolecular decomposition. Based on the experimental data that we're given, so the data, if you look at it in the book, is time and concentration. So it's concentration as a function of time. Based on that information, write the rate law for the reaction and determine K, the rate constant. We also want to predict what the AB concentration is. It's the concentration of this stuff at T equals 25 seconds after the start of this process. Okay. So the information that you're given is I've reproduced in this data table. Drawing a line right down the middle. Because if you look at the textbook, the information you're given is on the left of this line. All it is the time and the concentration. Now looking at the computer, you may not be able to read this. I mean, I can zoom in a little bit here just to give you an idea of what it says, but you can certainly find this information in the textbook, and really that's not even that good, and that's as close as I can get. So hopefully you're following along in the textbook, because you'll need to do that. You'll need to work on your computer anyway with this as we get into it here in a second, okay? But you're given time and concentration data of AB, okay? That's what you get. Now, from a study of chapter 13 of your book, all about reaction kinetics, we've learned about these so-called integrated rate laws. Integrated rate laws. And what these integrated rate laws are basically mathematical statements that we apply to either zero, first order, or second order reactions. And the neat thing about the integrated rate laws is they allow us to predict what the concentration of our reacting species will be at some point t in time. Now, the trick or the key to this is that the rate law, or the equation that we use to predict the concentration, changes, as does the reaction with a reaction order. Okay, so for a zero order reactant, we use this integrated rate law, which says the concentration of substance A at time t is equal to negative kT plus A0. That's the concentration of substance A at the start of the experiment, A0, okay? Or this is the concentration of substance A at some time t. We have our integrated rate law for a first order reaction, which tells us the natural log of our substance at the time t is equal to negative kT plus natural log of A at time 0. This is the concentration at time 0. This is the concentration of substance A at some point in time. These two equations look a lot alike, except notice the natural logarithm term. Okay, as we take that here, also take it over here. That's for a first order reaction. For a second order process in substance A, we can write the integrated rate law as follows. 1 over A sub t, that's the concentration at A at point t, is equal to kT plus 1 over the concentration of A at time 0. This is our second order rate law. Now, the reason why I've written these up on the board is to stress that each one of these rate law equations, integrated rate law equations, are written in terms of a y equals mx plus b line. Okay? In each case, what's written to the left of the equal sign is our y variable. In each case, our k is going to be our slope, and our t is going to be our x variable. Whatever comes along for the ride out here, it's going to be that b term, the intercept. Okay? So it's y equals mx plus b in every case. But the thing is that what makes up our y variable must change. And also, the slope, sometimes it's negative 1 times k, the reaction rate constant, and other times it's just equal to k. Okay? So the way you go about these problems when you're just given time or concentration as a function of time is you basically, or one approach to figuring out the rate law is you go in and you actually make graphs like I've done here in Excel. This is something I did on my computer and printed out just to sort of show you, okay? But I went in and actually made graphs of the data in accordance with these functions, okay? Now the first one up here, this is a plot of the concentration of AB in time. Just the concentration of AB in time, the data that's basically given in the data table in the sample problem. Right? Now why would I go about doing that? Well, if my reaction was zero order in my reactant, I would expect this plot of the concentration in time to be a straight line. So if that was a straight line for my zero order process, that would have been a zero order reaction. Okay, but we can see from the function that it's not a straight line. So this reaction is most certainly not zero order in reactant AB. Now we consider the next case. Maybe the reaction is a first order process. So we take the data, the concentration and time data, and we convert it to a form that should yield a linear relationship between variables if a first order process exists. So now here, my y variable is the natural log of the concentration as a function of time. Natural log is y, time is x. So in this middle plot, what I've done is I've taken the natural logarithm of the concentration, and I've plotted that as my y variable, and my x variable is still time. If that was a line, I would have a first order process. But if you can see the plot, it goes like this. It's not a line. Not a first order reaction as a result. So then I consider the second order in AB case. So what I've done here is I do 1 over A, the concentration at some point t, and I plot that versus my time. So I do 1 over the concentration as a function of time. And lo and behold, if I do that, 1 over the concentration of AB as a function of time, I get a straight line. So I'll put a check mark there. This reaction, in accordance with the data that I've been given, appears to be a second order process. A second order process in AB. So if I was writing the rate law, I would start by writing my rate constant K. And as usual, I would write the concentration of my reactant. Here that's AB. Since I know it's a second order process, I'd have to square it. And that's my rate law for this reaction. So if I was challenged with writing the rate law from the experimental data, this is how you do it. Okay, you go in, you figure out which plot is linear. But remember, to do that, you have to plot different things on the y-axis. If it's zero order, you plot just the concentration as a function of time. If it's first order, you plot natural log of the concentration as a function of time. If it's second order, 1 over the concentration as a function of time. One of these plots should yield a line. The one that does is the order of the reaction with respect to the reactant of interest, just like we talked about here, okay? So that's the trick to doing problems like this. Now, we're not quite done yet, okay? Because we're asked two additional things. One is we'd like to determine K, the reaction rate constant for this reaction at this temperature. So how are we going to do that? It turns out that it's reasonably easy to do that, okay? Notice the form of the equation for the line for our second order integrated rate law. If you look closely, where does the rate constant K appear? It appears right here. In this equation, K, the rate constant, is in fact our M, our slope of our best fit line. So all we need to do when we plot that function, 1 over the concentration is a function of time, from our best fit line through the data, extract out the slope, or otherwise try to measure it by rise over run, okay? And that's equal to K. It's that simple, basically, okay? So if we do that for this particular case, if we measure the slope of this line through the best fit line, or just otherwise try to compute it mathematically, we find that it's equal to 2.25 10 to the minus 2. 2.25 times 10 to the minus 2 is equal to our slope. That has units of per molar per second for this particular case to make the units work out. To make molar per unit, or molar per second units for the overall rate of the chemical reaction, right? So that is our K, that's our K value. So we're making a lot of progress, but we're actually asked one more thing. We're also asked, what is the concentration? Whenever you see the square brackets, think molarity or molar concentration. What is the concentration at 25 seconds, okay? So we're asked to figure that out. Now, how are we going to do that? What is the concentration of AB that's expected at 25? If we look at our data, we're actually not given a point at 25, so we can't just read a number off the chart, or that would be too easy. So instead, we're going to have to use our integrated rate law, because remember, what our integrated rate law does for us is it describes the concentration of our reacting substance at some period, at some time t, basically, okay, where we could plug in a value for t. So let's see how we can use this integrated rate law in forward direction. Okay? This would be sort of the typical usage of one of these. I should point out. What I'm going to do is I'm going to write my integrated rate law for my second order process, which tells me that 1 over the concentration, in this case that's really AB, 1 over the concentration at AB at time equals 25 seconds. So this is my desired variable. I'm going to solve this equation for that ultimately. But 1 over that variable is equal to KT plus 1 over the concentration of AB at T equals 0. That's my A0 term. It's the concentration of my substance at time equals 0 before any of this reaction started, okay? The initial concentration is right here. This is the concentration after some time, T. And which of these numbers do I know, which don't I know? I already mentioned that this term is going to be my unknown variable. So I'm just going to simplify this by calling that x. It's the concentration at time equals 25. My K is my reaction rate constant. I measured that from the slope of my line through the data points as 2.25 times 10 to the minus 2. Okay, so I know that number. My T is my time. It's after 25 seconds, which has consistent units as my rate constant. That would be the usual case to have seconds units there, okay? So I'm going to multiply that out ultimately. And I also need to add 1 divided by my initial concentration. Now, what was my initial concentration? Well, if I look back on the problem, there is a data point at time equals 0, and it was equal to 0.95, 0.95 molar. So I'm going to plug that in right there. Now what I'm going to do is keep working this problem and solve for x, my unknown variable. If I do that, I multiply this out and I get 0.5625. And I'm going to add that to 1.0526, which is the result if I do the division right there, okay? So then 1 over x is equal to 1.615. Solving for x yields 0.619 mole per liter. So my expected concentration at 25 seconds following the second order process for the decomposition of AB will be about 0.619 moles per liter.